Hello students, let's learn irrational numbers. In previous sessions, we learned terminating decimals and recurring decimals. There exist other decimal representations which are neither terminating nor recurring. Such numbers are known as irrational numbers. Let's look into one example. Decimal expansion is given as 0.120, 1200 and so on. If you observe this decimal expansion, it is not terminating. And not only that, the group of digits are not repeating. So we can say that it is an irrational numbers. Other examples for irrational numbers are √2, √3, √5, √7, etc. Students, let's prove √2 and √5 as irrational numbers. Before proceeding to that, let's have a recap of calculating square root of a given number by using long division method. For that, I am considering one example as calculating square root of 256. As you know, in long division method, the given number is divided into groups and each group will have 2 digits. So in this case, we will divide 56 into one group and 2 as one more group. As here we have 2. So let's start the number which is smaller than 2. So we'll take 1 over here and here also 1. So 1 into 1, it will become 1. Now subtract it, 1. Bring 56 down. Now double this digit, it will become 2. Let's take 6 here and 6. So 26 into 6. It's nothing but 156. Now the remainder is becoming 0. Therefore, square root of 256 is 16. In similar way, we can calculate square root of 2 and square root of 5. Now let's prove √2 as an irrational number. So we'll consider 2 point. We'll consider more number of zeros after the decimal point to check whether the decimal is terminating or not. As the first digit is 2, we'll start with 1. Here also 1. Multiply and write the product over here. It's 1. And subtract it. 1. Bring 2 zeros down. As these 2 digits are after the decimal point, we'll consider decimal over here. Now double this digit. It's 2. Let's take 4 here. Here also 4. It's 96. Subtract 4. Bring 2 zeros down. Now double this digit. It's 28. So we'll take as 1 and here also 1. The result is 281. Now subtract 119. Bring 2 zeros down. Double this digit. It will become 282. Let's take 4 here and here also 4. And the product is 11,296. I will subtract it and the remainder is 604. Bring 2 zeros down. Now double this digit, that is 4. So it will become 2828. So we will take 2 here and here also 2. The product is 56,564. Now subtract it. It's 3836. Bring 2 zeros down. Now double this digit. It's 28284. We'll take 1 and here also 1. So it will be 28281. Now again we'll subtract it and the result is 100,759. We'll bring 2 more zeros down. So when you observe this decimal expansion, it's not terminating and in the quotient the group of digits are not repeating. So we can conclude that √2 is an irrational number. Students, let's prove √5 as an irrational number. We follow the similar steps. So here first digit is 5. So we'll start with 2 over here and here also 2. Write the product. It's 4. Now subtract it. It's 1. Bring 2 zeros down. These 2 zeros are after the decimal point. So we'll keep a decimal point over here. Now double this digit. So it will become 4. Let's take 2 here and here also. It's becoming 84. Subtract it. It's 16. Bring 2 zeros down. Now double this digit. So it's 44. I will take 3 here and here also it is 3, and the product is 1, 3, 2, 9. Now subtract. Difference is 271. Bring 2 zeros down. Now double this digit. So it will become 446. So we'll say take 6 over here, and here also it is 6. And the product is 2679. Subtract. It's going to be 304. Bring 2 zeros down. Now double this digit. So it will become 4472. If you observe this number, even if you consider 1 over here, this number is greater than this. So that's the reason I will consider 2 more zeros here. As I am considering 4 zeros, I will take a 0 over here, and here also I will take a 0. Next we will take 6, and here also it is 6. And the product is 2683236. Now subtract it, and the difference is 35674. So if you observe this decimal expansion, the decimal expansion is not terminating, and digits in the quotient are, that is a group of digits, are not repeating. So we can say that root 5 is an irrational number. In next tutorial, we will see how we can represent these irrational numbers on number line. Thank you for listening.